Assalamualaikum and good day everyone. Today I will we will be presenting our project on the design and simulation of AC to DC full wave bridge rectifiers. The primary goal of this project was to use multi-sim software to design three distinct circuits capable of converting a high voltage AC input into specific lower voltage DC range. Our starting point for all three design is a 150 voltage AC input at a frequency of 50 Hz. The challenge was to demonstrate a practical application of step-down transformers and diode bridge configurations to achieve three very specific peak output voltage targets. First, a range between 16 volts to 18 volts. Second, a range between 10 volts to 12 volts. And finally, a lower range of 7 volts to 9 volts.
Assalamualaikum warahmatullahi wabarakatuh. My name is Firzah binti Muhammad Sarihi. My metric number is FB24020. So today I want to present about the I want to explain about the circuit of full wave rectifier within range 18 voltage to 16 voltage. So the first is place an AC voltage source and set its parameters to an amplitude of 150 voltage and a frequency of 15 Hz. So then add transformers within that I use is a ratio of 8, and then I arrange four 1N4007 silicon diodes in a bridge configuration, and then I place 1 kilo ohm across the bridge DC output terminals. Then I connect a ground reference to a negative terminal of the bridge to provide a common zero voltage point for the simulation, and then connect an oscilloscope as C1 to the primary winding or secondary output to monitor the input sine wave. Then I connect a second oscilloscope as C2 across the load resistor, and this will display the rectified DC voltage. Then I run the simulation and use the second oscilloscope to verify a peak voltage, and I get approximately 70.37367 voltage, and then within the necessary range of 18 voltage to 16 voltage, the full wave rectifier circuit that was constructed effectively transformed an AC input into a DC output voltage. By choosing a step-down transformer with a ratio of 8, the primary voltage at the secondary is lowered. Two diodes conduct in each half cycle following rectification through the bridge, producing a total forward drop of roughly 1.4 voltage. So I will explain about the full wave rectifier within range 12 voltage to 10 voltage. So the first is I maintain the AC voltage source at 150 V peak and 50 Hz. Then modify the transformer and I turn it to ratio to 30. Ensure the 4 and 4007 diodes and the 1 kilo ohm load resistor are properly connected. And then I run the simulation, adjust the oscilloscope to capture the waveform, and verify the peak voltage is at approximately 10.21 10.197 voltage, which falls within the range 12 voltage to 10 voltage target. And then the third circuit is full wave rectifier within range 9 voltage to 7 voltage. So you still maintain the AC voltage source parameters, and then change the ratio to I changed the ratio to 15, and then maintain the bridge rectifier and 1 kilo ohm load resistor connections. And then I run this simulation again, and I use the oscilloscope to confirm a peak of as approximately I got 8.65 8.661 voltage, meeting the range of 9 voltage to until to 7 voltage requirement.
To achieve these results, each circuit followed a consistent architecture. We utilized a step-down transformer to reduce the 150-volt input, followed by a bridge rectifier composed of 4 1 and 4 007 diodes. We chose the bridge configuration because it is high efficiency. It captures both the positive and negative half cycles of the AC signal, which effectively doubles the output pulse frequency compared to a half-wave rectifier. The critical variable in our design was the transformer turns ratio. By precisely adjusting these ratios, we were able to regulate the secondary voltage to meet our targets. Specifically, a turns ratio of 8 produced a peak output of 17.37 volts. A ratio of 13 resulted in 10.21 volts, and a ratio of 15 gave us 8.66 volts across a 1K load. These results were verified using multi-sims oscilloscope, which confirmed that the waveforms were stable and the peak values fell exactly within our required parameters. In conclusion, this project successfully fulfilled all design requirements. Through these three simulations, we have clearly demonstrated the mathematical and physical load relationship between the transformer turns ratio and the final output voltage. The result confirmed a fundamental principle of power electronics: as the transformer turns ratio increases, the peak output voltage decreases proportionally. This project served as a clear demonstration of how individual electronic components, transformers, diodes, and loads work together in a system to convert and regulate electrical power for practical use. Thank you for your time. That's all for our presentation.